Okay, so this is the last class of said strat. Hello. We're going to talk about, so we kind of been talking about how said strat affects like society. Today we're going to talk about records of climate, and that's going to be kind of the last class here. And just to make sure that you remember that the final exam is Friday, December 11th at 10:30. That's going to be kind of out of sight, out of mind for a little over a week, so maybe 2 weeks. So be sure you keep that in mind. Oops. Whoa, what the hell? All right, here we go. Okay, so some announcements. Okay, well, thank you for those who are joining remotely, and for those of you that are not, we'll just post this up on Blackboard, and you can watch it at your leisure. Not sure why I'm talking to you, because you can't hear me. Okay, so let's talk about climate. So last time we talked about extraterrestrial stratigraphy. Not going to review that. In all honesty, a lot of this material is not going to be heavily on the final. I'll send out a study sheet, though, next week so that you know what topics I do think are important from these lectures, but there's not going to be much there. These are just kind of like for quote-unquote fun. I think these topics are important and they're relevant, and that's why I'm talking about them. You may not share my thoughts, but that's what I think. Climate change is obviously a big issue, and it's kind of wrongly controversial. It shouldn't really be something that's so difficult to discuss. One of the major sticking points is really just the distinction between weather and climate. And some people, it's a sticking point because they legitimately don't understand it. And some people are just being deliberately obtuse. So weather is local and short-term atmospheric conditions at like a time and a place. So I look out my window right now, it's that good old shade of upstate gray, that gross, not amazing weather. Tomorrow it might be beautiful. I don't think it's going to be sunny, but it's going to be warmer. That's weather. It varies day to day, week to week on that kind of time scale. Climate is regional, so it's larger areally, and it's also longer term. So on the order of years, decades, centuries, millennia. And so I like this cartoon here. Climate is what you expect, and weather is what you get. So it is November in Oswego. There's a certain set of expectations that come for the weather in Oswego in November. That's the climate. Weather is what we actually get. Sometimes it's much colder, sometimes it's much warmer, sometimes we get a lot of snow on Thanksgiving, and sometimes we don't. That's the weather. Or another way to put it is weather, it tells you what to wear each day, and climate is what kind of clothes you have in your closet. Your closet's going to look very different if you live in Florida than if you live in New York. That's kind of the climate. And some people, again, deliberately mess these things up. So like this is one of the better examples. Senator James Inhofe from Oklahoma brought a snowball into the floor of the Senate. It was February, sometime around Valentine's Day. It might have actually even been on Valentine's Day. But he brought a snowball into the Senate because it was cold out and it was snowing in Washington, D.C. And it was like, aha, it's snowing in Washington, D.C. Climate change is a myth because it's cold out. That's weather. It's deliberately misconstruing weather as climate. Now, we also have to be careful on the other extreme because there's a lot of wildfires. There's a lot of large hurricanes this hurricane season. Pointing to any one of those weather events and saying that, aha, this is evidence of climate change is wrong for the same reasons. As the climate changes, those things become more likely, more probable, but you can't really point to any one event and say this is the result of climate change. It's just that the climate is changing, making those things more likely. So keep that in mind. And the whole rest of the lecture is going to be about how we know about climates of the past. It's pretty easy to reconstruct the climate for the past like couple hundred years because we have direct measurements, direct records of it. How do we extend that back further in time? So what we do is paleoclimatology. So paleoclimatology, just like paleontology, is the study of fossil organisms. Paleoclimatology is the study of fossil climate. Mostly temperature and humidity. That's kind of what we're really kind of driving after. That's the dominant factors of climate. They're the most important for ecology. So like if you want to compare like the tropical rainforest to the boreal forest, the main factors that control which occurs where is the temperature and the humidity. And so those are the most important from an ecological standpoint, from a biological standpoint, from a climatological standpoint. Climatology is a very complex relationship between the cryosphere, all the ice on Earth, the hydrosphere, all the water on Earth, even the lithosphere. So weathering alters the chemistry of the atmosphere, and so it impacts climate as well. And the biosphere impacts the climate also. So like organisms plants take in carbon dioxide, they release oxygen. The reason that we have oxygen to breathe in is because cyanobacteria over billions of years put that into the atmosphere for us. They altered the entire chemistry of the atmosphere. And so this is why climatology is important, and it's also why it's difficult. There's a lot of interacting pieces that interact with things in ways that we might not necessarily expect. But what this chart here is Phanerozoic climate change. So this is the climate of the last 542 million years. We can even extend further back into that, into like the latest parts of the Proterozoic, the Cryogenian, the snowball Earth period. As soon as snowball Earth ended, there was a massive evolution. The first multi-cell organisms, maybe climate, really triggered that evolutionary radiation. So there's a lot of these cool interplays between climate and life. But this is 542 years in the past, and there's a reconstruction of swings where it's cold and we get glaciations, and swings where it's hot and we don't. All the ice is melted and sea level is relatively high. How do we know anything about the weather the climate 500 million years ago? Well, that's what this lecture is about. It's all these records that we have. How do we know that in the past, the Saharan desert was wet? There are lakes and river systems in the Sahara that are now gone. It's all buried under sand. But during the formation of early human civilizations, the Sahara was a much different place. How do we know that? Climatology, paleoclimatology. So what are some things that we look at? So these are the different proxy data. And when I say proxy, proxy is something that stands in for someone else. Like if you're going to get your mortgage signed or something, you might have to assign a proxy if you're not going to be able to be there. A proxy is like a substitute. And so a climate proxy is something that records or reflects changes in those two variables that we really care about, temperature and humidity. It's not actually directly measuring those though. There's no real way to directly measure the temperature back in the Cambrian. There's no way to directly measure the humidity back in the Cambrian, but there are things in the environment that respond to the temperature and the humidity in ways that we understand, and those are the proxy data. Those are the things that we can look at. For example, we know how corals and other organisms respond to changes in ocean temperatures and ocean chemistry. They also build their shells out of the water and the elements that are in the oceans, and they sort of lock that chemistry up, and we're able to look at it later. Tree rings is a very popular one that we're pretty familiar with. Changes in pollen, just historical records going back like say 2000-ish years. Ice cores, these are all proxy data. None of these are direct measurements, but they tell us something about the climate. So let's walk through some of these different proxy data and what they can actually tell us about paleoclimate. So again, this is the one that we're probably kind of most familiar with, is tree rings. Sometimes it's called dendrochronology, chronology time from tree rings. It's dating and analyzing the thickness of these seasonal tree rings. And so this is a massive old tree that was cut for some reason. It's in a museum, and they've actually kind of counted the tree rings to go back in time, and they've labeled like very important events on here. So like, for example, it was planted in 1489 before Columbus landed in the Americas, or wherever the hell he landed. And then on here, they've actually got the birth year of the idiot who cut the tree down, so that's pretty funny. But you can basically count the tree rings, and you can get a year, so you can get a date. And then how that relates to the weather is that warmer, wetter years produce wider, less dense rings, and cooler, drier years produce narrow ones. And so if you're able to count and you know the exact year, and you're able to see the character changes, you can get the climate. This difference is much more pronounced in temperate regions. So the seasonality of temperate regions, like around here, where we have 4 seasons, that makes these tree rings a little bit more informative. If you go to the tropics, where the growing season doesn't really stop or slow down, it's a little bit more difficult. But what we do is we look at an individual tree, we look at its rings, and it only goes back, say, like 100, 200 years. 300 years is a really long-lived tree. Some trees can live to be like a couple thousand years old, but that's kind of a rarity. But we don't need the full record from one tree. What you can do is you can kind of get a record from one tree and then try to find an overlapping record from another tree. And we've actually been able to kind of piece together these barcodes and get a dendrochronology record that goes back about 12,000 years in certain places by looking at old trees that are fallen and stored in sediments and kind of barcode matching those rings up. So tree rings are very important and relatively easy to understand how this measures climate kind of indirectly. Another thing that we can use is paleontology, or Pollens. So the tree rings is kind of like how different plants respond differently. Different plant species like different conditions. Some plant species like really cold climate, some like really warm climate. And by looking at which species are prevalent in the area, that's a proxy for the climate. So like, for example, this big broad leaf is favored in tropical, warmer temperatures, and these smaller kind of jagged edge leaf species that have leaves like this are favored in kind of colder climates. And so if we look at the pollen grains that are stored in the sediment, pollen are like really resilient, really hard capsules of material. And there we can kind of map out which species belongs to which kind of shape of pollen, can map out the different grains. We can see how that changes through time. So like in a given area in the Paleocene was relatively warm. Coming out of the Mesozoic into the Paleocene, it was pretty warm. And then it kind of gradually cooled over time, entering into the ice ages in the Pliocene, Pleistocene, and Holocene. So what we see in the sediments is that the pollen over time shifts from the broader, leafier species of trees to the kind of smaller, more jagged species of trees. And we can see that in the record. We can also see it on the way out. So this is a record from a bog in Illinois. Justin works with some people carring bogs here in New York. They're looking at how the sediments respond to climate change, but you can also look at how the pollen responds to climate change. As the ice sheet retreats, there's a barren landscape left behind. The glacier kind of bulldozed everything and left this open space. The first thing that recovers are ferns and other mosses, relatively low-lying plants. But because it's still pretty cold, you're right at the edge of the ice sheet. The first thing that comes in are spruce trees. So you start seeing the evidence of spruce. A little bit higher up in the stratigraphic record, you start seeing ashes, elms, and eventually oaks. You're starting to get a shift from the coniferous cold weather forest into like a warmer weather deciduous forest. And then you might even see a transition into grasslands and things like that. So by mapping the different kinds of pollen, you can map how the environment was changing over time. And these pollen are stored in the sedimentary rock records, the pages of history. Another thing that we can see is that different plants perform photosynthesis in different ways. So there are C3 plants, which are most plants on Earth. They produce a 3-carbon sugar in their mesophyll. C4 plants are a little bit different. So things like corn do this. And then there's CAM plants, which are generally things like cactus that kind of do it at day and night. And again, different plants that perform photosynthesis differently prefer different environments. So cacti have a preference for drier climates, and these do not. And so if you're able to map those carbons over time, how that carbon content changes over time in the sediments, you can see which type of photosynthesis is being favored, which environment that probably is. And so this is kind of ways to look at like plants and that stuff kind of preserved in the rock record, in the sediment record. We can also look at the sediments themselves. So varves, we've talked about varves a little bit. Varves tend to form at like proglacial lakes or paraglacial lakes very near the ice front. But they're basically these annual rhythmites. So these kind of couplets of darker sediment, lighter sediment, darker sediment, lighter sediment, darker sediment, lighter sediment, this rhythmic deposition in very calm water. So there's no physical mixing of the sediments. There's also no biological mixing of the sediments, no bioturbation, because these are generally cold, generally sort of deepish lakes, commonly glacial lakes. What we see is that in the spring and summer, when there's all the runoff and heavier rains, coarser material makes it into the rock record. And there's much lower input during the fall and winter when everything's kind of frozen up. And so we see these thick, darker layers in the summer that are coarser, and we see these thinner ones in the winter. And we see this rhythmic kind of pattern. It almost looks like tree rings. If we did like a color shift to make this a little bit oranger or yellower, you might think that it's tree rings. It behaves very similarly. You can count the varves to get a date. You can look at the thickness to get some information about the climate. But it's basically the same thing as looking at tree rings, but you're looking at sediment rings. And we can look at a lot of them by doing cores. So this is a pretty standard core. You see kind of this point here. You kind of drive it into the ground and then kind of give it a twist. And then you pull up and you can get a core of the sediment. In some cases, you kind of disrupt the layers a little bit as you're doing this, but it's kind of the best you can do. Again, this is Justin does this in like Junius ponds. They take cores of sediment and they bring it back to the lab and they analyze it. You can look for patterns in changing clastic input, so sand to mud ratios. You can look at changing organic ratios. So is there more organic material in the system? Maybe a darker layer. Is there less organic material in the system? Maybe like a lighter layer. You can look at the kinds of microfossils that are present, again, especially like pollen or grass seeds, things like that. You can look at the chemistry signals. Are the chemistry signals changing? All these different patterns that you can look for in the sediment cores. Again, you're not directly measuring temperature. You're not directly measuring humidity, but you're measuring things that respond to changes in temperature and humidity in known ways. We know that if it's warmer and wetter, mechanical, physical weathering and chemical weathering are going to increase. You're going to have more input into the sedimentary layers. That's also stored in addition into ponds and bogs and marshes. It also happens in the open ocean. So you can use marine sediment cores to do the same thing. This is a drop core that they did, a piston core, and you basically take it in the lab, slab it in half, and you open it up and you look at it. You can count the layers. You can sample things from the layers, and it gives you some information about the climate if you understand how those things you're measuring respond to changes in the climate. Another thing that you can look at in the sediments are microplankton. So these are microfossil shells. Sometimes small shells are called tests. Animals build their shells from seawater. Calcium carbonate shells, CaCO3. As the organisms are building their shells out of CaCO3, or in some cases silica, SiO2, where they're getting the carbon, where they're getting the oxygen from, is from the seawater. And so they're locking in the chemistry of the oceans in their shells. And we can actually measure those. We'll talk about that on the next slide. But another thing is that certain organisms favor certain environments. So certain microfossils like to live in colder climates, and others like to live in warmer climates. And if you're able to understand those patterns, you can see shifts in those patterns, and you can detect shifts in temperature or detect shifts in humidity in some cases. Another thing is, in some cases, there's a very easily observable relationship. So example, in this particular foram and pachyderma, in warmer waters, the shell, the test, spirals dextrally. In colder waters, it spirals sinistrally. And so if you're able to look at the shell and the coiling direction, that's a proxy for the temperature. And so it's not just pachyderma, there's a lot of others that do it. Some Globigerinoes do it as well. And so this is a graph here of depth below the seafloor, and then percentage of these organisms that are found. And then they can also do like percent that are found spiraling in a different direction, and that helps you reconstruct temperature. But remember, as they're building their shells, they're also pulling chemistry elements out of the water column. And so stable isotopes become important. So isotopes are elements that have a different atomic mass. They have a different number of neutrons in the nucleus. So like there's oxygen 16 and there's oxygen 18. Oxygen 18 has 2 more neutrons. It's a heavier atom. Carbon comes in the carbon 12 flavor, then the carbon 13 flavor, and carbon 14 as well to a lesser extent, but it's not stable. So carbon 13 is heavier than carbon 12. It has 1 more neutron. And so there's a lot of different processes that happen in nature that fractionate these stable isotopes based on their weights. So like, for example, evaporation. The ocean has a set ratio of oxygen 16 to oxygen 18. But when it evaporates, evaporation favors the lighter oxygen. So as water evaporates, as H2O evaporates from the ocean, the H2O that has the lighter O16 tends to be evaporated. And then it forms into clouds, and then it rains out or snows out as ice. And so because clouds have more of the lower weight O16, so does snow, so does ice. And so during times of glaciation, there's more of the lighter O16 locked up in the ice on the continents. And so you've pulled out O16 out of the oceans, and you've left behind the heavier O18. And so if you have higher values of O18 in the ocean, that means that there's a lot of lighter O16 locked up on land. And so spikes in O18 in the ocean indicate cold climates. If we look at carbon, carbon exists in the oceans, and then it exchanges with the atmosphere. And again, it's the lighter carbon that tends to be favored in this process. Lighter carbon tends to be more likely to get into the atmosphere, and heavier carbon tends to be more likely to be left behind. And then plants take in the carbon dioxide and they build their tissue with that lighter carbon preferentially. They fractionate out the lighter carbon. And so lighter carbon-12 is more likely to be locked up in plant tissue. And so when you have really warm, really productive periods, you have kind of more of this, the 12 locked up. So if you have lower oceanic 13 values, there's less of the heavy stuff, more of the lighter stuff. That indicates colder periods. There's less lighter stuff locked in vegetation. When the atmosphere is colder, there's less vegetation going on. There's less primary productivity. There's less things using carbon dioxide. And so more of it's kind of left behind in the oceans. And so you actually get kind of the opposite pattern. And so these graphs here kind of show this over time. This is a climate reconstruction based on delta 018. You'll notice that positive departures go down. That's colder periods. Negative departures go up. That's hot periods. So they kind of flip the axes on this, which can make this a little bit confusing. But what we see is like right at the end of the Mesozoic, it's relatively hot. And then it cools down into the ice ages. We also see these ancient periods like in the Permian, when it was really warm, the end of the Devonian really warm, or it started the Ordovician really warm. End of the Ordovician, we have massive glaciers, and so we actually have these negative departures. But these are reconstructed from the shells of fossil organisms. The chemistry of those shells record the chemistry of the oceans at that time. We know how these things are fractionated now. We make the assumption the present is the key to the past, and we're able to reconstruct climate from that. This is how we get backwards from that 12,000 year tree ring, the 800,000-ish year ice core record. This is how we get back into the billions of years, is with these stable isotopes. This graph here is delta carbon 13. You'll notice that this is warmer, up is warmer, down is colder. Positive deviations in C13 is warmer, negative is colder, kind of the opposite of oxygen. So these are, you'll notice negative is down here, positive is up. Here negative is up, positive is down. This is hot, this is hot, this is cold, this is cold. And again, we look at that carbon isotopes in shells, and we know how that relates to temperature. And we can reconstruct the paleo temperatures. The oxygen isotopes and the carbon isotopes are somewhat independent from each other. And so when we use these together, we become more confident in the stuff that we're reconstructing. And so we're able to, again, confirm these glaciations in past history, the snowball Earth glaciation that potentially covered the entire Earth in snow and ice. So that's stable isotopes. We can also look at strontium isotopes. So different isotopes of strontium occur differentially in rocks of the crust and in rocks of the mantle. So like continental crust tends to have more strontium-87, and mantle and ocean basalt, more of the mafic stuff, tends to have more strontium-86. And so over time, as more continents are eroded, that would be putting more strontium-87 into the oceans. If we're eroding more mantle material or more basaltic material, we're going to be putting more strontium-86 into the oceans. And so what we see is that over time, this ratio between strontium-87 and strontium-86 kind of seesaws up and down as there's more continental erosion. So like, for example, in the Permian, we start assembling Pangea. There are these massive continental collisions, and we start eroding those. As we do that, we're putting strontium-86 into the seawater, and we get this negative departure. So we can see that in the strontium record. We can see evidence of the shifting climate. We can see shifts in weathering patterns, and we can use strontium-86 as well. You can actually kind of use this as age dates too. It's not a unique answer, but you can measure the strontium ratios in a sediment or in a rock. So like say you measure a ratio of this factor, it could occur at this time period, this time period, this time period, this time period, or maybe this time period. There's only a certain number of times in geologic history where that strontium value could exist, especially if you measure a really low ratio. That kind of gets you to only these two different time periods, and hopefully you're able to know whether it's Paleozoic or Mesozoic on other information, like fossils, for example. So you can actually use strontium as like a rough age dating technique as well. Another thing we can do is we can measure corals. So corals have annual growth rings, very similar to tree rings. In fact, again, if I recolored this image to look like wood, you wouldn't be able to tell the difference. You might think, oh, this is tree rings. Again, it works very similarly, but corals make their skeletons out of CaCO3 aragonite, a version of calcite, or similar to calcite, same composition as calcite. As it fossilizes, it mostly changes to calcite, but that isotopic signature of the seawater that they were living in is locked in. The strontium-calcium ratio is also locked in, and that's strongly temperature dependent. So if we slab a coral head, we can see the growth rings. We can also sample it and measure chemistry of the growth rings, and we can actually see changes in chemistry over time, and we can see that that's a proxy for temperature over time. And so this graph here is oxygen isotopes, positive departures, warmings, negative departures, coolings, and that's actually mapping the El Nino, La Nina fluctuation over geologic time. You can also do this with the strontium-calcium ratios. So there's a lot of different chemistries that record the climate in corals and other things that make their shells out of calcium carbonate or out of silica, SiO2. Another thing that, again, a common theme here is kind of looking like tree rings, things that grow annually that we're able to get an age date from. Speleothems do this as well. So a speleothem is like a stalactite or a stalagmite, something that grows in a cave. As that speleothem grows, you're precipitating carbonate. You're making rock. That rock, that calcium carbonate, locks in the chemistry that was in the source material in the water. And so you record the ages and the growth rings. Again, they're kind of seasonal. They grow mostly during spring and summer during the warm weather when there's a lot of groundwater infiltration. They are much slower during the fall when it's not raining as much, and during the winter when the groundwater might be there's less infiltration because it freezes. Another thing that it might record is that if the climate becomes a lot drier, speleothem growth might completely shut off. If there's no groundwater infiltrating into the cave, there's not going to be speleothem growth. And so you can actually see sometimes you can get these like hundreds of year hiatuses where there's no growth. How do you know that? Again, you look at the chemistry, you look at the dates, you're able to link that up. Another thing that happens if the cave becomes flooded, speleothems grow from little drips of water. The water evaporates, it leaves the rock behind, it leaves the mineral behind. If the cave's completely flooded, that also shuts off speleothem growth. And so this is a reconstruction here again of delta 018. Here it's delta 018 compared to VPDB. That means Vienna PD belemnite. It's this, well, it used to be a fossil sample, a belemnite, kind of a cigar-shaped squid shell. That was kind of the standard. They said that this is the standard for 018. This is the neutral value. Positive departures from this is positive, negative departures from this is negative. It's just a way to compare to a standard so that when you're writing a paper using delta 018, you've got some value to measure from. So again, we see changes in the 018 values responding to cycles in climate. We can date the medieval warm period or the Little Ice Age based on changes in these cave speleothems. Another layered deposit that we can use for climate is ice cores. So glacial ice is layered, formed from seasonal snowfall. Snow falls in the winter, builds up, builds up, builds up, compacts. In modern New York State, all the snow that falls melts, and so we don't actually build up glaciers anymore. Even in the highest of the high peaks, all of the snow that falls melts, and so we don't build up massive snowpacks that accumulate year after year after year. But if we did, snow builds up, a little bit melts, next year's snow builds up on top of it, it squishes down, more snow accumulates, it squishes, more accumulates, it squishes, and eventually it squishes and squeezes and compacts into an ice ball. Again, that analogy to taking a snowball, really smashing it down good to make an ice ball. In that process, you're actually locking little bubbles of air in the ice. And so this is an ice core. You can see the ice layers. Again, you can count these things just like tree rings. In some cases, you can even see like little ash falls recorded that you can actually use to date absolutely the age of that ring. But you can also see all these little flaws in here. If you blow that up, those are bubbles. Those bubbles are atmosphere that was between the snow grains when it was loose packed snow. As it squishes and squeezes, those little bubbles of atmosphere get stuck. And so these are little kind of paleo atmosphere. These are little time capsules of atmosphere that's in some cases hundreds of thousands of years old. We've got a good ice core record going back to about 800,000 years. You can actually directly measure the atmosphere. So we said before, you can't directly measure temperature, you can't directly measure humidity, but here you can directly measure the chemistry of the atmosphere because it's preserved in these bubbles. And again, we know the relationship of that chemistry to temperature. And so we can reconstruct patterns in ice volume over time, patterns of temperature over time, and we can see all these cycles, these natural cycles, over the last hundreds of thousands of years. It would warm up, it would cool down, it would warm up, it would cool down, warm up, cool down, warm up, cool down, warm up. Should be cooling down now. The solar parameters, the orbital parameters, those Milankovitch parameters that we talked about earlier, the eccentricity, the tilt, and the precession of the equinox, those combined, we should be having a cooling of the climate, and what we see is that climate's actually warming. Anthropogenic climate change, which we'll talk about in a second, our putting carbon dioxide into the air is overwhelming the natural signals. It should be cooling. We should be entering a new ice age. The ice sheets should be expanding based on orbital parameters, based on natural fluctuations. We should be coming out of this interglacial period and entering another glacial period. But our influence has overwhelmed that. So if we look at Phanerozoic temperature records, so again, how do we know this? How do we know the temperature in the Cambrian? How do we know the temperature in the Devonian? How do we know the temperature in the Triassic? We use these climate proxies. We can't measure them directly, but there's lots of these chemical signatures locked up in the rock record, recorded by organisms as they're living and as they're fractionating. And there's these little time capsules, these little breadcrumbs left in the rock record that help us reconstruct it. And so this is the Phanerozoic, the entire Phanerozoic, going all the way back to the Cambrian. There are several times in geologic history where it was much warmer. The Cambro-Ordovician hothouse. This is a time of massive evolutionary radiation. Middle Devonian hothouse, Permo-Triassic hothouse, Late Cretaceous hothouse. You see the values here, 26, 27 degrees C. So why do we talk about this as like an existential crisis? It's been this hot before. It's also been cooler before. The Late Ordovician icehouse, Permo-Carboniferous icehouse, the KT impact winter was much colder than it is now. So it's been a lot colder. It's been warmer. It's been colder. Right now, our temperature is kind of in the middle. So the big problem with climate change isn't the magnitude. It's not that it's hotter than it's ever been. It's not. It's not that it's colder than it's ever been. It's certainly not that. We're headed towards warmer temperatures, but it's going to be a long time before we reach the warmest temperatures ever. The problem is the rate. These rates are generally slow. These temperature fluctuations are usually slow. It's these natural orbital shifts, these very slow changes in oceanic spreading rates or continental collision rates, differences in weathering, slow changes in the climate, slow changes in the temperature. Organisms, the biosphere is able to adjust to slow changes. It's fine if it's hot. If it gets to the hotness slowly, organisms have time to adjust along the way. It's fine when it's cold. Organisms have time to adjust along the way to that change. Same thing like humans. If it were to get colder very slowly, we could adjust over time. If it would get warmer very slowly, we could adjust over time. It'd be very easy to respond to climate change if it was slow. When it's fast, that's when we get in trouble. And our rates now are very, very fast. The rate is the problem. Let's look back in geologic history to other times when the rate of change was very quick. Here's the Cambro-Ordovician hothouse, and we kind of drop off a cliff here into the Ordovician icehouse. This is a major disruption in the carbon cycle, a major shift in global temperature that occurred very quickly. What happened at the end of the Ordovician? A major mass extinction. Here's a very radical shift from icehouse to hothouse, a major shift in the carbon cycle. What happened at the end of the Permian? The Great Dying, the worst mass extinction in the history of the Earth. Here's another major change at the end of the Cretaceous as a result of the meteor impact or the Deccan Traps eruptions in India, probably a combination of both. What happened here at this radical, quick change? Again, a mass extinction. Here is our latest change, kind of this big hook upwards. Again, a massive disruption to the carbon cycle due to us taking fossil fuels that were going to stay in the ground for hundreds of thousands or millions of years, or maybe even hundreds of millions of years, and we're burning them quickly. We're putting that carbon back into the atmosphere. We're disrupting the carbon cycle. In the geologic past, when the carbon cycle was disrupted, bad things happened. So let's zoom in on the Cenozoic. Let's take a look at just the recent history. So if we look at all of human history, what we would call like civilization, the number keeps getting pushed back more and more, but it's tens of thousands of years. Really only like the last 12,000 years would we say like these are things that we recognize as like truly modern civilization, things like agriculture, fire, language, all of these things that mark modern human agriculture, modern human civilization, modern human society, developed in the Holocene, the last 12,000 years. If we look at geologic history, the Holocene is kind of weird. The Holocene is this relatively long period of time where things are stable. We developed civilization as we know it during this anomalous, stable period. And what we've started doing since the Industrial Revolution, and especially since 1950, the quote-unquote Great Acceleration, we've been dramatically altering the climate cycle, and temperature is starting to catch up. Our current rate of CO2 change is 100 times natural. So CO2 changes that in the geologic past took millennia are now happening in decades. And that's the problem here. It's not that it's hotter than it's ever been, because it's not. It's that it's getting hotter faster, maybe than it ever has. The rate is the problem. The rate that it's changing is the problem. And so anything that we can do to kind of slow that rate down, that's going to help. But there is already some debate as to whether we're entering into a sixth mass extinction. The current extinction rates on the planet, which again are very difficult to measure, it's very difficult to know how many species there are, let alone how many are disappearing. But we know that a lot of species are going extinct, and especially species that are sort of the quote-unquote canaries in the coal mine. So like frogs are very susceptible to climate change. Frogs are going extinct relatively quickly compared to other types of organisms. Corals are relatively temperature susceptible, relatively delicate to temperature changes. They are in trouble. So in the geologic past, we've saw huge disruptions in the carbon cycle result in massive swings in temperature, which result in mass extinctions. Is that where we're heading now? So there has been a push recently for the ICS, the International Commission on Stratigraphy, the people that made the geologic timescale. There's been a working group that's trying to assign now as a new epoch, the Anthropocene epoch, the age of human influence. So their argument is that the things that we're doing now, since about 1950, that would be their criteria for when it started, the things that we're doing now are radically altering the Earth. So all of the mineral extraction, all the carbon extraction, all the techno-fossils that we're making, like plastics, things that don't exist on Earth before, we move more material every year than all of the river systems on Earth. And so we're just radically altering our environment. And so there's an argument to define this as the Anthropocene. Like any rock epoch, it must be recognizable in the rock strata. So what would we use as the rock strata marker? One easy candidate is 1950s roughly, is when we started getting fallout from nuclear tests. These radioactive isotopes show up in the rock record. It also coincides when massive increase in the production of plastics occurred. That stuff's going to be stored in sediments. Massive population increases, massive increases in anthroturbation, humans moving rocks around, damming up major rivers, excavating major landworks. And a lot of the other time periods in the geologic timescale are defined by major life events. Are we entering into a sixth mass extinction? These are questions that this working group is trying to work on and address to define the Anthropocene period. Are we in the Anthropocene? This is sort of controversial. A lot of people have a problem with scientists kind of playing activist. To some people, this is somewhat distasteful, but really it's just a recognition that we have a dramatic impact on our environment, and we know the results of dramatic impacts like this from the rock record. We can't debate anymore whether climate change exists. It does. We can measure CO2 increases in the atmosphere directly. Whether climate change, whether global warming exists is non-debatable. The magnitude of the warming is debatable. How bad it's going to get, what the consequences are is debatable as well. What the policy reactions should be is certainly debatable. That's the conversation that we should be having, is what are we willing to do? What do we have to do? And how do we come together as a global community to accomplish this? That's the conversation that we should be having. And instead we're having the conversation of, I just brought a snowball in from outside, it's cold. That's not the right conversation. We're past that, or at least we should be past that. So are we in the Anthropocene? Is it actually different? Are we capable of creating a mass extinction recognizable in the rock record? I don't know, we'll see. The future is in your hands. So hopefully an educated populace is the key. And now you're very educated in said strat, hopefully. So that's the last slide. Again, thank you everybody for your participation in the class. I know this semester was far from ideal. It was very goofy and odd at times. Things didn't work out always like we wanted to. But overall, I had a lot of fun teaching the class. I hope you enjoyed taking the class. And I really hope that you're able to kind of safely enjoy your break. I may not have any of you for future classes, although some people are signed up for dinosaurs. But I did enjoy teaching you, and I hope that you're successful. And if I can help you out in any way, just let me know. Just because we don't have classes doesn't mean you can't reach out to me. So thanks for coming to my party. You rocked. Any comments, questions? Well, that's all. So if you don't have anything further, enjoy your break. Have fun.